forget, okay? Or toward the end of class, okay?
Yeah,
All right.
you forgot.
I know. I know. I'm horrible. I'm a horrible person. I know. Now, yesterday we left off with something like this, or we talked about it. Velocity over time, and we said, hey, look, constant velocity. That's constant, by the way. We said that we start off with this formula. We said x is equal to vt. This is under constant velocity. Your displacement is velocity times time. Okay? And when we say velocity right here, we mean the amount of velocity. We really just mean speed. Right? Because constant speed. Okay? Now, we also talked a little bit yesterday, right before you left, about how average velocity does not mean that you were traveling at a constant rate. It just means you went so far in so much time. Average velocity is distance traveled, displacement rather, divided by time. Okay? What's going on? Is she bothering you? Is she a distraction to you, sir? I understand that she could be. So maybe you need to get a handle on that. Okay? Uh-huh. I get it. I mean, if I was that distracted, maybe I just wouldn't sit there, because then maybe I would know that I couldn't concentrate. I don't know. I don't know. But that's just it. Now, average velocity. Again, you traveled this far. You've gone from here to here, and it took you this much time to get there. That's your average velocity. It's not very hard. Did you have to be moving it the whole time? Did you have to go in the same direction the whole time? It's just this is how long it took you to go there. This is how far you went. Done. Piece of cake. Now, because this is a algebra-based physics class, we can only assume two things. We have to assume, and as you know, when you assume, you make an ass out of you and me sometimes. Okay? It's the classic oldest line of all time. But you must assume constant acceleration. What do you mean constant acceleration, Mr. Groom? I thought acceleration was a change in velocity. Yes, you're not wrong. But what if it was constantly not changing? That would be zero. And that's perfectly okie dokie. If it's zero acceleration, there's no change in my speed, hey, that means it's constant velocity. Yeah. And so, we'll have that, but we must assume this in this class. Now, we will actually do a couple of examples where we will collect some data and do some stuff when it's not constant acceleration. That's okay, we can work around that because we have some data, some technology to help us. But if it's not constant acceleration, you have to have calculus, which is cool, but you don't have to do it in this class. Okay? So don't worry about that. Now, here's a question. So we just threw out the word acceleration. What does that mean, acceleration? Change in velocity over time. Okay. So what does that really mean? Well, in my car, I think of the accelerator pedal, which is the skinny one, you know. But that's one of them. It's actually, they're both accelerator pedals, yes? Yeah. Mm-hmm. But normally we think of the accelerator because we're speeding up, yes? But we're changing our speed. But in reality, you can change your velocity by changing the direction of the car, yes? So later on, when we're going in circular motions, later on, like our planet, for instance, going around the sun. Wait, I thought it was the other way around, Mr. Groom. No, I thought Kyrie Irving said it was flat. Okay, well. Anyway, we're going around and around and around, roughly the same speed, but we're constantly changing directions. So later on, we'll talk about centripetal acceleration and things like that. It's changing direction only in that case. In this case, but today we're talking a straight line. So when we say acceleration in this class, they're in chapters 1, 2, 3, well, anything not 6 and 7. How about that? Pretty much anywhere besides 6 and 7, we're talking in a straight line. We're talking about linear acceleration. We're talking about change in speed is what we're talking about. Okay? Well, that's interesting. Well, what if this is my velocity and this is my time? Hey, look at that. What is this? What kind of line is that?
It's a straight line.
Well, it's linear. And so it would follow this equation something like this. Yes, y equals mx plus b or something, right?
Something like that.
Something like that. That's a linear relationship. What do we call what is m? What's that about? How do you find slope, dear friends?
Rise over run.
I think it is the change in y. I know. But the way I've drawn this graph, it would be what? The change in velocity shot up over time, aka acceleration.
Magic.
So, acceleration. But Mr. Groom, Rx is time. You're not wrong. But Mr. Groom, my y is a v. You're right, it is a v. You see what I'm doing? I'm just playing musical chairs, right? This guy's going to play the part of y-intercept today. And this part's going to play the part of this and such. Now, here's where it gets a little wonky and weird. My y-intercept this time is 0, correct? But it could be this, correct? Or it could be this, or whatever. It could be any of those things. But when I did that, in both instances, both the y-intercept and the final y are both v's, are they not? Yeah. We're going to have to distinguish them somehow. What do you want to... What? I heard it.
Initial velocity.
And final velocity. Yeah. So, v sub f for final. And most books use v sub o. You could say v sub I. You wouldn't hurt my feelers, but your book uses v sub o. And that's one way to do it. Some years I only go about it this way. Some years I change it up. For instance, this. Literally, the definition of acceleration is the change in velocity over time. That is literally the definition, right, of acceleration. This is how I normally memorize it. But Mr. Groom, I feel like these are the same equation. They are. They are. It's so nice. Why would I have to memorize them both? Great question, Leah. You don't. Sister, I memorized this one because it's literally the definition of acceleration. During the test, you're like, geez, acceleration, that's changing velocity over time. That's what I just wrote. Other person goes, I like to do it this way. Hey, you do what you do you.
Well,
you do you.
Also, if you have one, you can find the other.
Well, of course, that's what I literally just said. Wait a minute, Mr. Groom. Couldn't I solve for v sub o equals? Feel like you could. If my pen would work, I could. And couldn't I solve for t? Yes, yes, and yes. But that's why we make you take Algebra 2 before you take this class. Okay. Memorize one of them. What?
I made Algebra 2.
That's why you're supposed to have taken Algebra 2 before you take this class. Now, this really is Algebra 1, right? This is an Algebra 1 deal, moving one back and forth. But you're going to want to, yeah. Okay, so thus far, we have these equations. And you're like, Mr. Groom, isn't this one really the same basic equation as this fella? I would say, yeah, if you know one of them, you know both of them, right? Ish. And we have this fella. Maybe I like to memorize it this way, but you do you. Just these two equations is all we've memorized so far. We're supposed to, okay? We're going to add 2 more by the time the day is over today. 2 more, that's all. And those will be the only 4 equations that you will need for this chapter.
Yay.
Yay. You're welcome. Now, here's a question for you. Here is a velocity over time curve. Mr. Groom, if this is velocity over time, and that's a nice linear function, yes? And we know that the slope is our acceleration, yes? The slope doesn't change on a linear function, right? It's just the same. It's 2 or it's 5 or it's whatever it is. If I were to take and graph acceleration versus time, what would it look like?
Quadratic.
Well, no.
Would it be linear?
It would be a constant function. Nice. Why? Because literally, this is what we're saying. The slope is a constant. It is not changing. It's 2 or 5 or 6. Let's say it's 5. Then down here, the acceleration was literally y equals 5. Boom. That's all it is. That's it. It's very straightforward. Is it not? Mr. Grimm, we never graphed the slopes of a linear function. No, but you're big kids now. So it didn't change. So we could graph y equals 5 or y equals 10 or what have you. Yes? That's cool. What do you know about this object? What do you know about it?
It's
Slowing down, it's decelerating, it's accelerating in a negative fashion, whatever. It initially had a positive velocity, and now it does not have any. Yes? Nice. If you were to graph its acceleration, what do you mean it sucks? Why does that suck? Aren't brakes a good thing? Aren't brakes a good thing?
Yeah.
I think so.
Not the way I do it.
It's not a plane, dog. By the way, I've never seen a plane just come in and nice, just calm. And if this was his height over time, and that was a plane,
That'd be scary.
that'd be a problem. I want to see this on my airplane. Thank you very much. Nice. By the way, I want to see this for my stopping in my car too, don't you? I do not want my car to look like this. That's because you hit the side of a wall or something. It's not good. I like nice rounded things on my accelerations and decelerations. Okay. What would the acceleration look like for this guy though?
It'd be under the.
It would be a negative because it was coming down. Yeah, I said negative slope. Nice. Right? Nice. We could play this all day. I'm not going to though. Now, let's go back and let's draw this picture here. And let's actually start from here. Velocity versus time curve. Mr. Groom, didn't you just 5 minutes ago, or yesterday, I forget when you said it, but didn't you just say that the area under a velocity versus time curve, didn't I hear you say that is displacement? Good job. That's exactly what I said. And then you're like, wait, I had geometry. I failed it, but I had it. This shape is, what is this shape here?
Triangle.
Well, no.
That's a quadrilateral.
Well, it is a quadrilateral. Could you be a little more? It's a trapezoid.
Yeah.
It's a trapezoid. And how do you find the area of a trapezoid?
Geometry is wild. With two triangles.
What? Say it?
You add both faces and divide by the height.
Well, no, it's close. Here's the deal.
Split it into triangles.
Was it? You could split it into pieces, but it'd be easier to say it. Something with the bases. Okay, first of all, who are the bases? Yes.
For the y-axis and
This guy here
the line
and
T.
this guy here, yes? Right? Here, those are the bases, correct?
Got you, yeah.
And so the formula is base 1 plus base 2 over 2 times height. Right? That's how you do it. That's how you found the area of a trapezoid back in the day. Now, when you take two things and add them and divide them, what are you really finding? Bless you. What are you really finding? Average of them, yes? The average base, if you will. Right? I got news for you. What is this value here, the y-intercept? What do we call that?
That's the V.
That's v sub O. And after you've gone for some time, how fast are you going? V sub F. So today, playing the part of base 1 will be V sub O. And playing the part of B2 will be V sub F. What? Divide by 2. So not an average base, friends, an average what? An average velocity. That's right. And then what is our height here? Time. Look, it's time. Time. Times time. And what will it equal? It will equal displacement. Yes. Now, a person could write it thusly. V bar times t. And you're like, we already knew that. We did. But we're not going to write it like this. We're going to shake it up a little bit. Okay, this is good, but it's nothing new that I didn't already know, yes? But let's do this instead. Do you recall on the previous page somewhere, we wrote this equation. V sub f is equal to who? Well, I usually write it V sub o plus AT, but you could do AT plus V sub o, right? We had that equation somewhere, did we not? Let's substitute, shall we? So V sub o plus V sub o plus AT, because that right there is V sub f, right? I'm going to pull the 1/2 out front if you don't mind, because I feel like it. Okay? And then times it by t. Are you with me? So this piece here is right here, and of course the half is out front. And then the t is, well, it's right here. Yes? Yay! Does he see it? Yeah. Okay. Okay, but let's look at it, see what you get here. How many V sub O's do I have? That's correct. Plus an AT times a T. Yeah, I'm not done, but do you see that? If you distribute, you're going to get a V sub O plus 1/2 of an AT times a T. And if you distribute the other direction, you're going to get this. Now, this is how I remember it, so I'm going to write it a little different. I'm going to do 1/2 AT squared plus V sub O T. This, friends, is our equation. Notice that on this problem, this right here, I don't need to know V sub O, yes? Or V sub F, I mean. I don't need V sub F on this problem. The way I did it previously, up here somewhere, it was the average velocity, meaning I need to know the first one and the last one. Well, if I didn't know them, I could go find it, of course, but it's just way easier to know just acceleration, time, and initial velocity. This equation right here is one of our biggies. I'm going to go write it with the others, wherever they went. Come back. Where did you go? Where did I put you? Crap, I lost him. Well, they're here somewhere. I don't know where they went. I'm going to write them on a new page. So again, you don't need to copy this one down, but this one and this, that guy right there, this guy, and this one right here. There's one more coming, but those are the three biggies so far. And they're not very hard. I refer to this one as the grand poobah myself. It is kind of the biggie. It's kind of like on the Flintstones. Fred was the grand poobah of the Moose Lodge or something. I don't know. I can't remember. I think it was something like that. It's a big deal. Okay. Guess what happens here? Check it out. If A equals 0, what happens if A is 0? What?
The velocity is constant.
The velocity is constant, but look what happens to this equation if the velocity is constant, friend. Whoosh! And you get the initial velocity, which is just the velocity, because there's no acceleration, so it ain't changing. Voila, there it is. Nice. But Mr. Groom, what if V sub O is 0? Hey, what if it is, dog? What would that happen? Remember our graph looked like this a minute ago? That's because we had an initial height of some V sub O. What would it look like? It'd look like that. Nice. There you go. All of these things, and what would happen to this equation? This equation, that would go away then, yes. Nice. Yeah. So a variety of things can happen. And we can use them all. The grand poobah is a big deal. Now, let me just note here. that up here on this guy, it's optional. You could have an initial displacement. For instance, you could, like your 0 could be home here in St. Helens. Let's just say St. Helens proper is a dot on the map, and that's where your 0 is. Scappoose is +8, and then Portland +30 or whatever, okay? Whatever. And you're in Scappoose, and you're headed to, at time equals 0, you are in Scappoose. So your initial displacement might be +8, okay? Of course, if there is no initial displacement, that x naught is 0, and just screw it, it's gone, okay? This is where you started, and this is how far you've traveled in some amount of time to get to a new location. Again, this piece here, totally optional. It might be there, it might not be there. Okay? Mr. Grimm, is that true down here? It's true down here as well. It is also optional. You could have started somewhere else. Now, I will say this, in flat dimensional stuff, it's kind of boring. But later on, we get to dropping things off buildings and shooting things up in the air and what have you. This x naught becomes a y naught. It becomes an initial height. And if you jump off the ground, like, look, I'm going to fall off the ground. It's really hard to do that. It's boring. But if you go, I went cliff diving from 30 meters up, hey, that's +30. Okay? And so later on, that's going to be a bigger deal. Okay? But for right now, it's optional. It might be there. It might not be there. Whatever. Okay? Now, I would like to look at this formula a little bit more. Somebody, was it you that said it? Break it into 2 pieces? Who said that? You said that. Well, you said it's not triangles. It's triangle and a rectangle. Check it out. Back in the day, a person could have done this. But friends, look at this equation right here. This guy right here is how far you would have gone if you hadn't accelerated, yes? Friends, that's this area right here. But I wasn't. I was accelerating. So this piece here is the top piece. And you're welcome. Okay? That's it. Now, I think that's helpful to understand it when it comes to doing the problems. Just freaking use the formula. But I think it's helpful to see it, like geometrically speaking. I think it's helpful to see it. This is a rectangle. It's exactly what we did to start off with. We kept a constant rate. This is how far we would have traveled. But because we were accelerating, we added this much more to it up on the top of it. So when someone says, hey, break it into pieces, that is true. It's a triangle and a rectangle. Maybe that helps you to see the picture better. Maybe not. I don't know. Yeah? Yeah? Hey, so you depress me some days when you sit there like that. Are we boring you? Do I need to dance a little more or something?
Yes.
All right, here we go. Yeah, good? 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 Now, let's do a problem, shall we? This will be my first crappy drawing of the year. It's a big wheel. You can draw it or not draw it. I don't care what you do. Totally up to you. So a little toddler doing his thing. Got his Ray-Bans on. That's nice. Now, cool. Well, actually, I'm going to start at his front tire. There we go. He's going to go 10 meters. He is currently traveling at, 3 meters a second. How long does it take? This is a very straightforward one. Did I say anything about him accelerating? I did not. And so, of course, the time is simply going to be, well, I'm going to start off with this equation, x equals vt, right? Heard nothing about acceleration, so I have to assume he's traveling at a constant velocity. How long does it take? Well, I don't know, 10, 3, t is equal to 3 1/3, and done. 3 1/3 seconds. Well, he's not going very far, and he's moving right along on his little big wheel. Huh? His little big wheel. Nice. That's easy. Well, that's cool. Piece of cake. Got it? Are we good? We good? Let me come back up here. Oh, sorry. I did. Sorry. I'm getting excited. As soon as I start to draw pictures, I get kind of fired up. Nice picture, by the way. Nicely done. Yeah? Let's light it up, shall we? Nice. Now, let's suppose that this little feller, actually, let's do this. I just found out I could do this last year. This is kind of exciting. And I got a new pen. This new pen's a little bit different, but I think I can do it. Yeah. Oh, yeah. Copy. Give it to me. There we go. Paste. Come on. There you go. Boom. Cool. All right. There we go. He is currently traveling at 44 meters per second,
Holy crap.
That's a fast time.
which is, you know, 100 miles an hour,
No, 14.4.
or thereabouts. He comes to a stop in 20 seconds. What is his acceleration? Clearly it's negative. How do I figure this out? Now, okay, listen, there's two ways to do this problem. No, wow, there's several. Okay. Conceptually, there's two ways to do this problem. Some people, I'm going to do this for you. There's two ways to do this problem in that some people go, oh, let me see my formulas. It's not a bad way to do it. It's not my favorite way. My favorite way to do it is this. I want to know, well, I want to find acceleration, yes? What is the definition of acceleration? That's right. That, my friends, is the relationship. So when I see this, I think to myself, you have one already?
Yeah, I grabbed one yesterday.
Oh, well, I'll take it back then. Okay.
And if you look right here,
And again, we will not have covered it all. So first of all, you perfectionists, you know who you are. You cannot do them all this week. And, well, couldn't I spend hours studying or anything? You could, but please don't. Go until you go, I don't know how to do this problem at all, and then stop. And pick it up on Monday. Okay? By the way, somebody asked about this the other day. Mrs. Kersley's youngest son drew this picture for me after I told him what I wanted it to be. Guys, I envision physics as a crock pot. I love stew. I love stew. But you cannot take stew meat, put it in the microwave, and have it turn out anything that you could eat. You can't chew it if you microwave it. It's, yeah. You put it in and you stew it. And it marinates and it cooks in its own juices for hours. It'll take you a couple weeks. I will lift the lid every day, chop some onions in there, little carrots, give it a stir, put the lid back on it. Okay? At the end of the chapter, we should have a nice conceptual stew up there. Awesome. Nobody gets this crap right off the bat. You have to actually think about it and stew on it. Huh? Nice. Now, friends, this is the relationship. What, I ask you, is our final velocity here?
0.
Yes! What's our initial? 44. Hey, what's the time? 20. That's negative 2.05? No, that's not right. Negative 2.2. Negative 2.2, huh? Negative 2.2. And what would that be measured in? Meters per second. Come on, right. Per second, which we normally in this class will write and say as meters per second squared. Okay? The reason for that is because this is seconds over 1. Oh, go away. And when you invert and multiply, it's meters per seconds times 1 over seconds. So it's meters per second squared. Nice. Here's a question. How far did he travel? I don't know.
We could graph it.
We could graph it, but that seems goofy. Feels like to me we need one of our two equations. Either this guy. What's wrong with that guy? There's no acceleration. The dude was accelerating. or this guy. Again, we need a displacement equation. It's one of those two right now. And he's accelerating. Well, it ain't this one. Okay. Now, someone could say, couldn't I use this one? Oops, I'm sorry, not x bar, you idiot. X equals v bar t. In theory, yes. Was he not going 44? And did he not go 0 at the end? 44 plus 0 is? Oh, it's 44. And 44 divided by 2 is 22. That's where I was going with that. Okay, so in theory, you could use this guy. I get in the habit of using this one. So 1/2 times negative 2.2 times how long? 20 squared plus 44 times 20. This one cracks me up. Some people are going, that's going to be weird, Mr. Groom, because this part here is going to be positive. You're right. This part's going to be negative. Interesting, right? Because that's a negative piece here. So when you add them together, or when you add the pieces together, you're going to end up with a, well, it's going to end up, this guy on top is quite a bit larger than this piece, but a positive plus a negative is going to end up with a positive value. But he's going to actually travel some distance. What do you get? What do you get for an answer here? 440 meters this little feller travels. Nice. So a little over a quarter mile. But he was going 100 miles an hour. So there you go. Now, again, over here a person could go, well, wait, didn't we say his average velocity was 22? Yeah, we did. Times 20. Am I shocked by this? I'm not. Okay, I'm not. But what I am saying is this. I, most of the time, will use this formula because, to me, that formula it just speaks to me. It speaks to me because there's acceleration in this problem. Okay, and I think I like this guy. Okay, cool. But again, it should work either way. I mean, it'll always work if you don't screw it up. That's one of my catchphrases too. It's not up here though. If you don't, it'll work if you don't screw it up. Okay. Now, here's a question for you. Again, our little fella. Once I do them, I usually keep rolling on them. Last year it was Cambria was in every picture last year. Here's my Cambria. Giant goofy grin on her face every time. And look, now our intrepid explorer is going to do this today. You know, I need a new muse this year, whatever. Now, here's my question to you. Again, the little feller's doing 50 meters a second now. No, actually, no, let's do this. 50 miles an hour. Oh! Let's make it easy. Let's make it tricky. 55 miles an hour. Ooh, we're going to have to convert, Mr. Groom. We'll do that in a moment. We'll do that in a minute. Here's my question. He comes to a stop in 30 meters. How, or let's see, what's that? Yeah, how fast was, not how fast, duh. What was his acceleration? What was his acceleration? And when you're first learning these things, a person, I think, is a good idea to write some of this business down. And I don't need them all, and I don't even need all but one of them. I just kind of like to keep note of what do I know here. Okay? And I'm going to know some of these on every single problem, yes? That's going to help me decide, especially when I first get started sometimes, which equation to use. Okay? Obviously, if I pick an equation, I better know everything but one of the variables, yes? Because that's kind of what algebra says. You only solve for one at a time. Okay? So if you ever get stuck, I think it's helpful to write that down or make a list or make me just mark them over here. Here's X and here's V sub O, or V sub O, and so on. Okay? Obviously, V sub F is 0 and things like that. But notice what's missing here? Time. Time is missing. That could be a problem because every problem we have, every equation we've had thus far has what in it?
Time.
Oh, crap. Oh, crap. But let's start off with this. Let's do 55. Let's convert this over. Better start here. Per hour. Of course, there are 1 hour, 3,600 seconds. And what do I want to say? 1,600 meters in a mile. Cancel, 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 cancel. And you got what? 24.42. And I'm not shocked by that because 50 would be 22-ish. And so you're like, it makes me happy, and I'm happy. Yay. Meters per second. Cool. Now, what am I going to do? This is what I'm going to do. I'm going to spare you the disgusting algebra. You're welcome. But what I'm going to do, oops, there's a T there, stupid. There you go. But what I am going to do is this. I'm going to show you, I'm going to start with these two equations, and I'm going to make them into one. I want to get rid of time. So watch me solve for time here. Yes? Now I'm going to substitute this fella here and here. Okay? Now I'm going to go ahead and write it in just for a moment. Right? Okay. Yeah? What the heck? I'm screwed. I'm just going to go with the thing. I'm just going to blow that baby up. I'm just going to blow it out and do it. I mean, I feel like some algebra today. How about you? I mean, come on. You can never do enough algebra. So, on the top, if I distribute this out, because it's really v sub f minus v sub o times v sub f minus v sub o, right? Right? Because when I say this thing's squared, I really mean this times this. Right? So that's going to give me v sub f squared minus 2 v sub f v sub o's plus v sub o squared over a squared. And I'm going to have a v sub o v sub f minus a v sub o squared over a. Isn't that awesome? It's great, actually. This is really going to be fun when we're done. But notice the time's gone now. This equation will be very helpful. Frequently, it's very tough to go out there and keep an eye on people going by really fast. Here, stop me on a stopwatch. It's hard to do. But if I knew how fast they were going, which I can do with a radar gun, real good, and I can see when they went by, I can know how I can mark off 300 meters or whatever on the sidewalk. That's any idiot can do that. Time is not really that important to me. Okay, I can solve for that later on if I wanted to. All right, watch me. The A's cancel there and there, yes? One of them? Yes? Nice. Now, let's distribute this half all the way through, okay? No, wait, don't do that. I changed my mind. Let's multiply everybody by 2. And not just 2, 2a. So watch me multiply this entire equation by 2a. A because that gets rid of my denominator, yes? And 2 because it gets rid of that half on the other side. So it's going to be 2ax. Now if you times this guy by 2, this half goes away there, yes? And the a on the bottom goes away. So I'm going to be left with v sub f squared minus 2v sub f v sub o's. Uh-oh. No, there it is. I got it. It was freaking me out. I was like doing the math in my head and going, that's not going to work. But I got it now. There we go. Plus, now again, this guy actually gets multiplied by 2 over this fella, yes? So there's going to be plus 2 of these guys and minus 2 of these fellas. I did it right. Check it out, friends. Whoosh, whoosh. Yes? Yes? Hey, look, this plus this is a negative v sub o squared. Okay? And I just usually memorize it like this. That's how I normally memorize it. But you're welcome to memorize it in any order you like. This equation here will help us out on the problem we just did. We said that the guy was going to be 0 at the end, yes? Because it came to a stop. He was going 24.42 to start with, correct? By the way, don't screw this up. Later on, you'll have negatives to start with. Negative, anything squared is positive in this class. You will not have an imaginary velocity. That's weird. You'll have a real velocity, so any real number squared is positive. Well, unless it's 0, in which case it's non-negative. Okay, it's non-negative. Don't screw that up, okay? You know how it is. Your boyfriend dumped you. You're on the Twitter, the face pages. You're crying. You're absorbed with your new show about vampires, whatever. And you literally type into your computer, -6 squared. The computer says -36. You're like, okay, cool. Wrong. Don't screw that up, okay? It is a huge pet peeve of mine. I've made the mistake. I've been swamped and thinking about other things and been troubled by that. Don't screw that. Don't be that guy or gal. Okay? Now, 2, what was his acceleration? Hey, I don't know it. That's cool because this is algebra. And how long did it take him to come to a stop? 30. Boom. Boom. Let's do this thing. Watch me. What is 24.42 squared? Will you help me out there? It's positive something or another.
596.3.
So I'm going, how much?
596.3.
So I'm going to subtract it to the other side. And that's going to equal 60A divided by 60. A equal, I don't know, what is that, 9-ish?
9.94.
-9.94. Again, meters per second squared. So that guy right there is our 4th equation. From now on, we're pretty good with the 10:05, right? From now on, we're pretty good with those 4 equations. And again, let me write them right here. If it were me, here's a tip that Mr. Groom would do. I would probably have an equation sheet, and I'd get either one of those little fancy deals for like this is important little sticker deal on my notebook. You know what I'm talking about? That little fancy. You go on Home Depot, or not Home Depot, look, that's the place. And you get these little sticker doohoos that stick out like this. This is a big effing deal, like Joe Biden would say. Or a sticky note, or like folded over, but it's kind of a big deal. And you'd have these guys written down somewhere where you can quickly reference them. But again, one should really memorize them. Oops, I almost screwed it up. And this fella. And I would have them written down somewhere where I could get to them easily and reference them. Those are the 4. Like, what about the average ones, Mr. Groom? If you want the average ones, knock yourself out. All right? The average velocity one, you know, we wrote this down earlier. That's true. By the way, we actually looked at it like this on day 1. It's the same deal, though. But if you like that, help yourself. If you don't, don't. Average velocity could also be thought of as this. We did this earlier. If you like that, hey, knock yourself out. But again, every single one of these assumes constant acceleration, which could be 0. But these 4 right here, that's the only 4 I would bother memorizing. That's all I would bother memorizing. The rest of it, I would just leave it alone. These down here are basically conceptual as far as I'm concerned. I don't need to memorize them. I know what they mean. These 4 right here, big deal. Look at who the cat drug in. Nice. This is exciting. I was just thinking of you this morning, actually. Yeah. All right. So anyways, I want you all to have a nice weekend. I don't want anyone to cry.